Hi everyone. We are now beginning the last section of our course and we will focus our attention on regressions. This particular video will focus on simple regressions, so one variable situations. Let's start with just a graphical observation. So what differences do you observe when comparing the following graphs? Of course, there are definite similitudes between them, but some elements kind of stand out. The number of points in each scatter plot seem very different. The equations of the lines through the scatter plots are different as well. And the notation that was used to represent the linear correlation coefficient was different. In the first graph, we used rho, whereas in the second, we used R to represent the correlation. So the first graph actually represents a scatter plot for an entire population of diamonds whose price and number of carats are used as the dependent and independent variables respectively. In contrast, the second graph represents a scatter plot for a sample of diamonds whose price and number of carats are used as the dependent and independent variables respectively as well. Although the equations for each line through the scatter plots are similar, they are not identical, nor are there linear correlation coefficients. As we can see, both the slopes and the y-intercepts for the two lines slightly differ, as do the correlations. So sampling does not only affect averages and proportions, as we saw in the previous section, it may also affect the trend that we observe between variables. The relationship that variables x and y have to one another is only approximate when using sample data, whereas populational data provides the true relationship. A first distinction should then be made. First of all, in terms of notation, we're going to use Greek symbols, beta 0 and beta 1, to describe the y-intercept and the slope for the best fit curve obtained from populational data. We will use Roman letters B0 and B1 to represent the y-intercept and the slope for the best fit curve obtained from sample data. Beta 0 and beta 1 are therefore parameters, whereas B0 and B1 are estimators of beta 0 and beta 1. The values we will find for B0 and B1 will depend on what individuals were selected to form the sample. Because B0 and B1 are subject to sampling errors, we will obviously not always trust the values that they convey. For example, x and y may be linearly dependent, and yet the sample best fit curve may lead us to think otherwise. In this graph, we have the blue trend, which is that of the population, which clearly increases, and in red are sample points that were selected, and the best fit curve through the sample had no particular trend with a slope of practically 0. Likewise, x and y may be linearly independent, and yet the sample results may lead us to think otherwise. In this graph, the populational data in blue has no general trend, with a best fit curve whose slope is roughly 0. Amongst the population, the individuals in red are those that were sampled, and they will give you the impression that there is an increasing trend to the relationship between x and y. In statistics, the last of these errors is the one we want to avoid as much as possible. It is the biggest error to conclude that a relationship exists between variables when in fact it doesn't. So sample results will be submitted to hypothesis testing before we can acknowledge that a regression is significant. So what we will be testing is the value of the parameter beta 1. Remember that beta 1 is the slope of the best fit line that we would obtain from populational data. If beta 1 is different from 0, then we can conclude that there is a trend, so a relationship where values of x changing causes y to change as well. Here are the hypotheses that we will confront. On the one hand, we'll assume that beta 1 is 0. In other words, we'll assume that x and y have no particular relationship, unless we can reject h0 to accept h1, in which case we'll conclude that beta 1 is significantly different from 0, and a trend is observable. Now to conduct the test, we'll use Excel templates, which will provide us with our estimates for beta 1 as well as the p-value. The templates will look somewhat like this one, where in the data folder, you will enter all of the variables you are interested in. The dependent variable will be placed under y, and the independent variable will be identified with a 1 and will be treated as the x component. In the results section, the output will give you the estimated value for beta 1, so b1, as well as the estimated value for beta 0, which we call b0. The output will also provide the p-value for the test taking place on beta 1. Based on sample results, one can conclude there is sufficient evidence to reject h0 if the p-value is under 5%, which was the case in our previous slide. With a p-value of 0, any level of alpha, 1, 5, or 10%, would not have been surpassed. We can therefore accept that beta 1 is not 0, and conclude that the regression is significant. This would mean, in the context of the problem that we were observing, that the price of a diamond is definitely affected by the number of carats it has. Furthermore, you can use the equation to estimate the price of a diamond when its number of carats is used. Here is the equation that we got from our table. B0 was the constant in the output. B1, $8,881, was the slope from our sample results. Now, interpreting the results may force us to be slightly careful. For B1, 8,881 is the estimate that we have of the average price of diamonds when one additional carat is added to the diamond itself. We say average because remember that the equation represents the trend line through roughly the center of the scatter plot. It is not the individual price of each diamond. B0, the y-intercept, is minus 3,774, which means we estimate that the average price of a diamond or of diamonds that have 0 carats are $3,774 negative dollars. Obviously this doesn't make sense, but then again, a 0 carat diamond doesn't exist. So this estimation would be considered an excessive extrapolation. Predicting the value of y can be done also with the template you'll be provided with. Under the prediction file, you can enter the value you wish to give to your independent variable. Output will give you the predicted value, in this case $6,884 for this diamond. two different confidence intervals are given. One for the value of an individual diamond, or in fact the confidence interval for an individual diamond, so $4,333 to $9,434, and another interval for the average price of all diamonds that would have 1.2 carats. So the average of this group of diamonds, 6,784 to 6,983. So some warnings we have to keep track of. We have to avoid interpreting the value of the slope obtained from a regression that is not proven to be significant. That's why we do our hypothesis test on the slope. You have to avoid interpreting the constant when the context does not allow the independent variable to be zero. You have to make predictions on y within the domain of observed values and never go outside of that domain, which would be called an extrapolation. A word on performance. So a significant regression does not mean that the regression is efficient. Indeed, a regression equation can demonstrate that a trend exists between y and x. However, it doesn't mean that x will be a good predictor of the value of y. Here's a representation of this, where on the left we have a scatter plot where salary is expressed in terms of an employee's experience. On the right, the same salary is expressed in terms of the employee's age. Notice how the scatter plot on the left is much more tightly represented to the best fit line, whereas the second cloud of points is more dispersed. So the line is a better predictor in the first case than in the second. The coefficient of determination, r squared, can be used to measure the performance of a linear regression. In the first graph, r squared was 0.691, which means that 69.1% of the variance in salary is the result of an employee's experience. In the second graph, r squared was 0.3623, meaning that 36.23% of variance in salary can be explained or justified by the employee's age. R squared measures, therefore, the proportion of the variance for a dependent variable that can be explained, predicted, anticipated by